So far, we have seen some of the important results in the theory of complex valued functions. For example, we have seen what is Cauchy-Garsa theorem, what is Cauchy's integral formula, what is Cauchy's integral formula for the derivatives. We have also seen consequences of these results, and most importantly, we have also seen that how these results help us in evaluating contour integrals. Now, in this module, we are going to turn our attention to one important property related to any function. So this is about maximum and minimum value of a function. So for example, in the theory of real valued functions of one variable in calculus, we have seen that there are some methods, for example, first derivative test, second derivative test, which can help us in finding the maximum and minimum value of a function. Now, if we talk about complex valued functions, then there is no concept of ordering in the set of complex numbers. So there is no well-defined order in complex numbers. In other words, if I have two complex numbers, let's say 1 plus iota and let's say 3 minus iota 100, then we cannot say that 1 plus iota is bigger than 3 minus 100 iota or smaller than 3 minus 100 iota. So there is no ordering, well-defined order in the set of complex numbers. So we cannot talk about the maximum and the minimum values of the function of complex variable. So what do? We talk about the maximum and minimum value of the modulus of a complex valued function. So that's what all this module about. So we want to talk about, we want to understand the behavior of the maximum and minimum value of the modulus of a complex valued function. So this is the maximum modulus principle, which is our main and fundamental result of this module. So it says that if we have an analytic function, and of course we have to impose this condition that it should be a non-constant, because if it is constant function, then there is the discussion of minimum and maximum value doesn't really make sense, and it is a trivial situation. So we have analytic function and it is non-constant in a domain D, and remember what is a domain D? It is an open set which is also connected. Then this modulus of this complex valued function does not attain a maximum value at any point z0 in D. Okay, so this main result is basic in this direction where we want to understand the maximum and minimum value of the modulus of a function. So this result says that the maximum and minimum value, or in this case only we are talking about the maximum value, and as a consequence we will see the minimum value as well. So the maximum value at any point, so maximum value does not exist at any point in this domain D. So when we say domain D, it means this light blue region, and the boundary is not included because it is a domain, which means it is an open set. So basically we can also denote this boundary with this dotted line. Okay, so the result says that if the maximum value exists, then it cannot be at the interior of D. Okay, so more precisely we can say that if we have an analytic function which is non-constant in the bounded domain D, okay, and if f is continuous on the closed region R that consists of D and all its boundary points B, then this modulus of complex valued function assumes its maximum value and does only at the boundary point. Okay, so let's say we have this region. So what are the conditions? So first of all, we are imposing a condition of the function. So first condition is f is analytic and non-constant in the bounded domain D. Okay, so this is the domain D, and remember in this case the domain D does not include this boundary. Okay, f is continuous on the closed region R. So what is this closed region R? So closed region R is equal to D union the boundary of D. Okay, so this shaded region is the boundary of this domain D. Okay, and f is continuous on this closed region R that consists of D and the boundary points. Okay, so analytic on the domain D and continuous on this set R, which is domain D union its boundary points. Then the consequence of these assumptions is that the modulus of this complex valued function assumes its maximum value, okay, so and does so only at the point z0 at the boundary. So the point is the maximum value exists only at the boundary, and under these conditions it definitely exists. Okay, so let's say this is the domain D, and the maximum value of the function exists. Okay, so under the conditions that we have imposed on the function, that it should be analytic on this set D, on the domain D, and continuous at the set D union B, where B is basically the boundary. Okay, so under these conditions this modulus of this function exists, and it only exists at some boundary point. Okay, so there will be, let's say, some boundary point z0 where this function attains its maximum value. So let's talk about some examples. Consider this function sin z, which is a complex valued function, and the region that we have chosen in this example is this rectangle region in the complex plane, where x varies from 0 to pi and y varies from 0 to 1, and we want to find out the points where the modulus of this complex valued function sin z has the maximum value. And according to the maximum modulus principle, it should happen at some point at the boundary of this region. In other words, it should be some point on this red line, okay, which is the boundary of this region. Okay, so first of all, we can only say that the maximum value exists at the boundary if this function satisfies the condition of the maximum modulus principle. So for example, if this function is analytic, yes, it is analytic on this blue region R, which is basically a domain. It is open and it does not include the boundary, which is the red line. And secondly, it should be continuous on all of this region R. Okay, so region R is basically we can say that the interior of R union the boundary of R. Okay, so we are denoting the boundary with boundary of R and interior with interior of R. Okay, so it should be continuous on this whole set R. If this happens, then the maximum, according to the maximum modulus principle, only exists at the boundary of this region. Okay, now let's try to actually find out what is the point where the maximum value of this function exists. So in order to find the maximum value, let's find the square of the modulus, which is the sine x plus iota y mod square, and we know from our previous discussion that sine of x plus iota y is equal to sine x cosine hyperbolic y plus iota cosine x sine hyperbolic y mod square. Okay, so there is iota in here, so it's a complex number, and we know how to calculate the modulus of a complex number. Okay, so there is no square root because we are taking square over here, so just take the square and add the first and second coordinate, and then we can just add sine square x sine hyperbolic square y and sine square x sine hyperbolic square y. Okay, so we are just adding and subtracting these two terms. So if we multiply sine square x with sine hyperbolic square y and this sine hyperbolic square y with sine square x, then these terms will just cancel out each other. Okay, so we are just adding and subtracting, and then we are combining them in the following way. So what is the main benefit of doing this? That we can use the result cosine hyperbolic square y minus sine hyperbolic square y is 1, and cosine square x plus sine square x is equal to 1, and hence we have the square of the modulus of sine z is equal to sine square x plus sine hyperbolic square y. Now this sine square x is a non-negative function, sine hyperbolic square y is a non-negative function, and if we want to talk about the maximum value of the modulus of sine z, so we need to understand where the maximum value of sine x and sine hyperbolic y will exist. So our next task is to understand in this, of course, domain, in this region R, where is the maximum value of sine x and where is the maximum value of sine hyperbolic square y. Okay, since we have the following function. Okay, let's talk about sine x. We know the graph of sine x is given by this, and from here we can easily observe that the maximum value between 0 and pi, okay, of course between 0 and pi, the maximum value exists at pi by 2. Okay, so whatever the point of maximum value is, Okay, so maximum value of sine z mod is, it should have the x coordinate to be pi by 2. Okay, and the function sine hyperbolic square y is an increasing function, and hence between 0 and 1 the maximum value should be at 1. So from this graph we can see that this is sine hyperbolic square y, and the maximum value should exist. So this is 0, this is 1, and in this interval the maximum value is at y is equal to 1. Okay, so using these values we can easily see that the maximum value of this modulus of f of z is when x is equal to pi by 2 and y is equal to 1, and hence the maximum value exists at the point pi by 2 and 1. So where is pi by 2? So pi by 2 is somewhere over there and 1 is somewhere over here. So we can say that this is the point which is pi by 2 1 where the maximum value of this function exists, and it of course fits with the maximum modulus principle, which says that the maximum value can only exist. Okay, so it exists first of all, and secondly it only exists at the boundary, and this pi by 2 1 is a point at the boundary of this blue shaded region. Okay, so and p lies at the boundary. Okay, so the function this modulus of f of z has maximum value at the boundary and at no other point. So this is the important point. So this is one of the important points that this maximum modulus principle says, that it cannot happen at the interior. Now let's talk about another example. It's a very simple function. It's a linear function. It's a linear polynomial, and the domain is basically this S, which is a open set. So this is of course connected as well. So any two points are connected and the boundary is not included. Okay, so no boundary, so that's why it is open. Okay, and what is the closure of this S, which includes the boundary? So this is, this blue region is the boundary. Okay, now we want to talk about the maximum value of this function, but only on this region S bar, and the claim is that the maximum value is mod of A plus mod of B, and of course we want to find out the point, the exact point where the maximum value of this function is attained, and hence we will try to see that if it is at the boundary or not. Of course it should be at the boundary according to this maximum modulus principle, but in this example we want to actually find out that point. Okay, now the calculations are relatively simple. We know that we are working in this S bar, in which case the modulus of z is less than or equal to 1, and hence we have this property. And of course we want to talk about the modulus of f of z. So modulus of f of z is modulus of az plus b, which by triangle inequality is less than or equal to az plus modulus of az plus modulus of b, and according to another property, simple property of modulus, this is equal to mod of z into mod of a plus mod of b. Now over here observe that the mod of z is less than, strictly less than 1 if you are in the interior of this circle, and this is exactly equal to 1 if you are at the boundary, and the maximum value will only happen when the mod of z is equal to 1, and otherwise when you are inside the circle then it will be strictly less than mod of a plus mod of b. So this kind of fits with our claim that only the point at the boundary is going to be the point where this function is attaining its maximum value. Okay, so moving on, we need to actually find out that point. Okay, so now we need to show that this value occurs only at the boundary of S. Now let's see how to show that. We need to actually find out exact that point at the boundary, and of course since a and b are arbitrary, so that point the description of that point z naught should depend on a and b. Okay, so consider this point z naught, which is e raised to power iota t naught, and the value of t naught is given like this. Okay, and in this case of course it is some point at on a circle, because in this case mod of z naught is equal to 1, so it is some point at this circle which is the boundary of this region S. And in this case we choose this t naught to be argument of b minus argument of A. So what is the main benefit of that? So we can prove the following, that argument of A z naught is equal to argument of A plus argument of z naught, once again according to the properties of argument that we have discussed in our earlier discussions. So this is going to be equal to argument of A plus argument of B minus argument of A, because argument of Z is equal to argument of B minus argument of A. So we are just using this condition, okay, that we imposed on T naught. So and of course argument of A will be cancelled out with argument of A, and argument of A Z naught is equal to argument of B. Now what does that mean? So that means that these two numbers, which is A Z naught and B, they have the same argument, and which means geometrically is that both these numbers lie on the same ray in this complex plane. Okay, so for example A Z naught will be somewhere over there and B will be somewhere over here. Okay, now or you know it can be somewhere over else as well. Okay, so this is the situation. Now what does this imply? So this implies that the modulus of f of z naught is equal to modulus of A z naught plus B. We are just using z is equal to z naught in the definition of f of z. So this is equal to modulus of A z naught plus modulus of B, which is by this definition is equal to modulus of A plus modulus of B, because when you are calculating, and we know that the modulus of z naught is equal to 1 because it's a point on the circle. So this is just equal to this thing. Okay, now what does this imply? It means that the functional value at z naught is equal to mod of A plus mod of B, which is basically the maximum value of the function. So this point z naught is a point on this circle, which is the boundary of S, where this maximum value of the function is attained. Now using this maximum modulus principle, we can also talk about the minimum value of the modulus of a complex valued function, and hence this so called minimum modulus principle. So under the same conditions, that is, the function should be continuous on the closed bounded region R, and it should be analytic and non-constant throughout the interior of this region R, and if f of z is not equal to 0 anywhere in R, then the minimum value of this modulus of f of z occurs at the boundary of R and never in the interior. So the idea or the connection between the maximum and the minimum modulus principle is very simple. If you talk about the maximum value of the modulus, then you take this, and if you want to talk about the minimum value of the function, then you just consider 1 over mod of f of z, and then the whole discussion will be directed towards the minimum value. Now that's the end of our discussion on the maximum and the minimum value of the modulus of a complex valued function.